Okay, so this is a quick lecture on the driving forces. So basically, there's three things that can happen when you put reactants together. And then the first is nothing can happen at all. And if that is the case, that means that there are no favorable conditions for the reaction to occur. The next is that you could put them together and they can react instantly. Condition for that reaction. And then the third thing is you could put them together and they could react, but it takes a long time for them to react, or it requires some sort of input of energy. You might have to heat the reactants to make it go. And if that's the case, that means that the reaction probably has a very high activation energy. It still has a favorable condition, but it has a high activation energy that is required to make it go. So you might be wondering, what are these conditions that I'm talking about? And the truth is that there's only one condition, and that is Gibbs free energy. But we're not going to study Gibbs free energy specifically. We're going to study the parts of Gibbs free energy. So the two conditions that I'm talking about here are something called entropy and enthalpy. So entropy is measured with an S. That delta S is a change in entropy. And entropy is the measure of disorder of a system. So if you have, cars lined up in a parking lot versus cars moving on the freeway, cars in the parking lot have less entropy than the cars on the freeway. The cars on the freeway are all moving different speeds. They're changing lanes, whereas the cars in the parking lot are just kind of lined up, neat in a row. None of them are moving. So entropy is a measure of disorder. More disorder, more entropy. What we're going to do are use the states of matter to predict entropy changes. And we're going to look at the states of the reactants and compare them to the states of the products to see if entropy is increasing or decreasing in a system. You might think that the universe favors a decrease in entropy, having things become more orderly, but the truth is the universe really favors disorder. So anytime the universe is getting more and more disorderly, that is something that is chemically, and we can say thermodynamically, favorable for the universe. That's something that's probably going to happen. So when we consider the entropy changes in our chemical equations, looking at states of matter, right, you can imagine that gases have the highest entropy. And then after that are going to be things that are dissolved in water. So aqueous ions would be next. And then we would have pure liquids. And then we would have solids. So solids, of course, having the least amount of movement, are going to have the least amount of entropy. So we want, the universe favors an increase in entropy, meaning the products are going to have a higher entropy than the reactants will. And when we have a number that is a big number minus a little number, a change in entropy that is positive in sign, and we don't really care about the magnitude of the number at this point, so we're not going to deal with actual numbers. We're just going to look at sign. Entropy is increasing, and that's what the universe likes. Enthalpy. Enthalpy is heat. We use an H to represent heat, and of course a delta H is a change in enthalpy, and we still measure that by products minus reactants. And the universe favors a system where the energy is being lowered. So when the universe has potential energy that's being turned into kinetic energy, it likes that. So when the energy of when the enthalpy of the products, if it's energy lowering, is going to be less than the enthalpy of the reactants. That's what the universe likes. So if we're solving for the change in enthalpy, the products would have a low enthalpy, the reactants would have a high enthalpy. That would lead to a value that is a negative number. And of course, this is an exothermic process. When the reactants start with a little bit of energy and they end up with less energy, that's what we call an exothermic reaction. Okay, so we can summarize this in the little chart that's in your notes here. If we have a negative enthalpy, that's an exothermic process. The universe does not like that. If we have the universe does like that. If we have a positive entropy, it's becoming more disorderly, so gases are being formed. The universe likes that. So this reaction is always spontaneous. There's nothing that we can do to stop this reaction from occurring. Okay? I'm missing something there. If we have a system that's got a positive enthalpy and a negative, something happened to this here, and a negative entropy, meaning that it's getting more disorderly. It's getting less disorderly. Then both of these conditions are unfavorable to the universe, and the universe will never allow that reaction to happen, so it will be never spontaneous. Another way of saying that a reaction is always spontaneous is to say is at all temperatures. So when we have conflicting conditions, so if the enthalpy is negative and the universe does like that, but the entropy is positive or negative and the universe does not like that, then that really depends on temperatures. So this reaction is sometimes spontaneous. And I will actually allow you to just tell me sometimes, or sometimes I'll ask you to tell me under what conditions of temperature. So this is sometimes spontaneous, and it occurs at low temperatures. If you have a high temperature, this reaction is not likely to occur. If we have a positive enthalpy, the universe doesn't like that, but we have a entropy that is favorable to the universe, the same thing occurs. The reaction is sometimes spontaneous, but the temperature conditions change. It's spontaneous at high temperatures. So I'm going to do a couple of practice problems with you that I would expect you to do with the driving forces. On this first one, I'm asking you just to predict. Is it always, never, or sometimes spontaneous? I'm not even asking you for the low or high temperatures, although sometimes I will. So what we're going to do here first is determine the change in enthalpy. Is this reaction exo or endothermic? And the way we're going to do that is to look to see where the heat is being listed. Here we can see that the heat is being listed as a product, which means that this is an exothermic reaction. Heat is going out. The sign for enthalpy when heat goes out is negative, and the universe likes that. That's a favorable condition to the universe. And then to determine the entropy, we're going to look at the state symbols. So here in this reaction, we have 2 moles of sodium gas, 1 mole of chlorine gas, and that's making 2 moles of solid. So here on the reactants, we have 2 moles of gas forming 2 moles of solid. So in this case, entropy is decreasing. The sign for the change in entropy is going to be negative, and that is an unfavorable condition to the universe. The universe does not like that. So this reaction with conflicting conditions is sometimes spontaneous. If you wanted to add a heat caveat to that, you could tell me that it is spontaneous at low temperatures. The next example, we have heat and it's listed here in the reactants. So here, enthalpy of reaction is positive. That's an endothermic process. That is not favorable to the universe. Again, to determine entropy, we're going to look at our state symbols. We have 1 mole of gas, 2 moles of solid, and 1 mole of gas. So here we have 2 moles of solid, 2 moles of gas. And then in the products, we have 2 moles of gas. Now the number of moles of gas is not increasing, however, the solid is going away. And when the solid goes away to make a gas, which is really what it boils down to, we have a solid turning into a gas, that means that entropy is increasing. Which means the sign for the change in entropy is positive, and the universe likes that. So again, we have conflicting conditions. The universe likes the entropy and does not like the enthalpy, so this will be sometimes spontaneous. And again, if you wanted to give me a temperature, you would say that that occurs at high temperatures. We can see this last reaction. The heat is a product, so that is exothermic, and that is something that the universe likes. We are going from solid to 2 moles of aqueous ions, so entropy is increasing, which means the sign for the change in entropy is positive, and the universe likes that, so this reaction is always spontaneous. Another way of saying that is that it is spontaneous at all temperatures. I want you to do the rest of these that are in your notes and ask me questions about them tomorrow. We'll go over them first thing. Okay, and then I'll do one of these with you, or maybe 2 of them, where we determine what is the driving force. So in this type of problem, you are told these reactions go, and you need to figure out, is this going to be the driving force of enthalpy? Is the driving force the entropy? Or is both of them? So really the question that's being asked here is, which one of these conditions is favorable to the universe? Is the enthalpy favorable? Is the entropy favorable? Or are both of them? So if we look at the first example, we can see that our heat is a product that's exothermic. The universe likes that, so this is favorable to the universe. Now if we look at our state symbols to determine entropy change, we have solid, aqueous, yielding solid, aqueous. There is no change in entropy. That's not favorable to the universe. The universe doesn't like that. So that means that because we know this reaction goes, it is not the entropy driving it, but it is the enthalpy that is the driving force for the replacement of copper by iron. And you guys have actually done this in a lab in class. So we know this reaction occurs, even though the entropy is not something that's good for the universe. It's because the enthalpy, the heat, makes it go. Okay, so if we look at the second process here, we have solid water going to liquid water. You guys, this is the chemical expression for ice melting. We can see that that requires energy. This is endothermic. Endothermic is unfavorable to the universe. But we have a solid turning into a liquid. Liquids have more entropy than solids, so entropy is increasing. And therefore, entropy is the driving factor here. Okay? So what you're going to do here is just determine what factor is favorable to the universe, and that will be the driving force of the reaction. And if they're both favorable, you would say, hey, they're both driving the reaction. Okay, so finish these in your notes tonight. We will go over the answers tomorrow, and if you have questions, please let me know.